given function values at equally spaced points, say x0, x1, etc., etc. So, we try to develop numerical differentiation methods. How are we going to do this? We write out the method that approximates, say, a derivative of the function f, say the first derivative, involving function values at some points, and require that the unknown constants which appear in this method are determined in such a way that the resulting numerical differentiation method is exact for polynomials up to certain degree. This is how we determine the coefficients which are unknown. So, let us consider the following 5-point formula. Suppose, say, I am interested in considering a 5-point formula for f dashed of x, for estimating f dashed of x. Say, let us take the formula as I want f dashed of x to be estimated in such a way that it is a1 times f of x minus 2h plus a2 into f of x minus h plus a3 f of x plus a4 f of x plus h plus a5 into f of x plus 2h, say, divided by h. Say, I want to construct a formula for f dashed of x in this form. So, what are the points that are involved? X minus 2h, x minus h, x, x plus h and x plus 2h, and the information about the function values are available to me at a set of these points. So, I take a linear combination of these values, function values, and what is my requirement now? I determine these constants a1, a2, a3, a4, a5 in such a way that this method, which I call as double star is exact for polynomials of degree up to, let us see, how many constants do we have? There are 5 unknown constants to be determined. So, we require 5 conditions to determine these 5 constants. So, we require or we impose the condition that the method double star is exact for polynomials of degree up to, say, 4. So, we have a constant polynomial, the first degree, the second degree, the third degree and the fourth degree polynomials. So, they will give us 5 conditions to determine these 5 constants. It is enough to ensure that the method double star is exact for polynomials given by f of x is equal to 1, x, x square, x cubed and x to the power of 4, because the expression involves only function values and they appear linearly. And secondly, we would like to obtain this method in such a way that it should be independent of any shift of origin. And so, we consider this method with x is equal to 0 and derive this method. And thirdly, the method that we are going to obtain should be independent of the step size h, and therefore, we take h is equal to 1 in this method and then obtain the numerical differentiation method for approximating f prime of x. So, we take f prime x must be of the form a1 into f of h is 1 and x is 0. So, f at minus 2 plus a2 f at minus 1 plus a3 f at 0, a4 into f at 1 plus a5 into f at 2. So, let us substitute f of x given by these and arrive at the conditions. When f of x is 1, then this gives you f prime x is 0, and therefore, it will give you a1 plus a2 plus a3 plus a4 plus a5. So, that gives you the first equation. When f of x is x, f prime x is 1, and that will give you a1 into f of x is x. So, f of minus 2 will be minus 2 plus a2 into f of minus 1 plus a3 into f of 0 plus a4 into f at 1 plus a5 into f at 2. So, that gives you the second equation. When f of x is x square, so f prime x, so f prime x is what? We have taken x to be 0. So, f prime evaluated at 0 is given by the right hand side. So, when f of x is x square, f prime is 2x evaluated at 0. So, it will be 0, and that is equal to a1 into f of x is x square. So, f at minus 2 is minus 2 the whole square, a2 into minus 1 the whole square plus a3 into 0, a4 into 1 square plus a5 into 2 square. Then when f of x is x cubed, it is 3x square. So, at 0 will give me 0 equal to a1 into, it is x cubed. So, minus 2 the whole cubed minus 1 the whole cubed plus a3 into 0 plus a4 into 1 cube plus a5 into 2 cubed. And finally, when f of x is x to the power of 4, 4x cubed is its derivative. So, at 0 it will be 0. So, that will give you minus 1 into, a1 into minus 2 power 4, a2 minus 1 power 4, a3 into 0, a4 into 1 power 4 plus a5 into 2 to the power of 4. That gives you the fifth equation. So, we have 5 equations to solve for a1, a2, a3, a4 and a5. So, when you solve these equations, you end up with the solution as a1 is equal to minus a5 equal to 1 by 12 and a4 is minus a2, and that turns out to be 2 by 3, and a3 is 0. So, this tells you that you have a differentiation formula for f prime x such that it is 1 by h into a1, a1 is 1 by 12 into f at x minus 2h plus a2, that is minus 2 by 3 into f at x minus h plus a3, that is 0, plus a4, which is 2 by 3 into f of x plus h, then plus a5 minus 1 by 12 into f at x plus 2h. So, it is important to see the class of functions for which this method is valid, that is one thing, and also to see the order of accuracy of this method, which essentially means that we have to obtain the error term in this approximation. So, let us work out the details of the error that is incurred in approximating the first derivative f prime of x in terms of the values of the function, right, involving 5 points. So, error in approximation so the error expression is given by f prime of x minus 1 by 12h into f of x minus 2h minus 8 into f of x minus h plus 8 f of x plus h, and then I have minus f of x plus 2h. So, I should compute the difference between f prime x and the terms on the right hand side. So, this will be equal to f prime x minus 1 by 12h into, let us use Taylor's theorem and expand this function f of x minus 2h. So, it is f of x minus 2h into f prime x plus 2h the whole square by factorial 2 into f double prime x minus 2h the whole cube by factorial 3 into f triple prime x, then plus 2h the whole power 4 by factorial 4 into fourth derivative at x minus 2h the whole power 5 by factorial 5 into fifth derivative at x. I can write down some more terms. Let us stop at this and then see whether we are able to obtain an expression for the error term. Since I have truncated here, this is going to be the error term in expanding f of x minus 2h about the point x. So, I present the error in terms of the fifth derivative, say at psi. Then the next term is going to be minus 8 times, or I can take it to be x because I do not know whether I can truncate it here or should take more number of terms. So, I shall just write this and say plus etc. and then continue to write down this term, which is minus 8 times f of x minus h f prime x plus h square by factorial 2 f double prime x minus h cube by factorial 3 f triple prime x plus h power 4 by factorial 4 into fourth derivative at x minus h power 5 by factorial 5 into fifth derivative of x plus etc. Then I shall write down the next term plus 8 into f of x plus h f prime x h square by factorial 2 f double prime x minus h cube by factorial 3 f triple prime x plus h power 4 by factorial 4 into fourth derivative at x. Then minus h power 5 by factorial 5. This is f of x plus h. So, all the terms will have positive signs, fifth derivative at x plus etc. And then I have the last term, which is minus f of x plus 2h. So, it is f of x plus 2h f prime x plus 2h the whole square by factorial 2 f double prime x plus 2h the whole cube by factorial 3 into the fourth derivative at into the third derivative at x plus 2h the whole power 4 by factorial 4 into fourth derivative plus 2h power 5 by factorial 5 into the fifth derivative at x plus etc. So, we have written down all these terms using Taylor expansion. All the other derivatives which appear in the expansion have coefficient to be 0. The fifth derivative has its coefficient to be non-zero, and the error is given by h power 4 by 30 into the fifth derivative evaluated at psi. Where does this psi lie? It lies between x minus 2h and x plus 2h. And so, we have a numerical differentiation formula for f prime x given by f prime x is 1 by 12h into f at x minus 2h minus 8 f at x minus h plus 8 f at x plus h, and the last term is minus f at x plus 2h, and the error term is plus h power 4 by 30 into the fifth derivative at psi, for psi lying between x minus 2h and x plus 2h. So, f prime x can be estimated in terms of the values of the function at these points, which will be given to us in the table of values, and the error term is given by this expression. So, the error is of order of h to the power of 4, and the factor which appears here, namely the fifth order derivative, tells you the class of functions f for which the first derivative can be estimated using this formula, namely f, f prime, f double prime, f triple prime, f 4 prime must be such that they all are continuous in the interval x minus 2h to x plus 2h, and the fifth derivative must exist in the open interval x minus 2h to x plus 2h. So, you get an information about the class of functions for which the first derivative can be approximated by the first term from the expression in the error term. So, we have now used method of undetermined coefficients. We shall just recall what it is. We propose a method for approximating a derivative of the function, and then we say that this method must be exact for polynomials of certain polynomials up to certain degree. Namely, we impose the conditions in such a way that there are as many conditions as we have unknowns appearing in the proposed formula. And so, depending on that, we make the method exact up to polynomials of certain degree and determine these unknown coefficients and compute the error that is incurred in that proposed method, which gives us the order of accuracy of the method, and in addition it provides for what class of functions we can use the proposed method to estimate that particular derivative which has been given or which has been obtained using this numerical differentiation method. So, we have a number of such formulas or numerical differentiation methods for evaluating various order derivatives, which can be derived by proceeding in the manner in which we have obtained this particular method. So, I shall give you one or two such methods and you can try to work out the details yourself. So, another observation on this method is that this method is called a central difference approximation for the reason that you have been able to estimate the derivative at this point x in terms of the function values at x minus h, x minus 2h, x plus h and x plus 2h, which lie symmetrically on either side of this point x. So, this method is known as a central difference approximation method. So, as I said, I shall give you one or two such methods, and I would like you to obtain those methods by working out the details. So, show that the second derivative f double prime can be approximated by a 3-point formula we had already derived this using Taylor expansion earlier, and we have showed this result, but now I want you to obtain this method by the method of undetermined coefficients. So, how do you start? You say that you propose a method which is of the form 1 by h square into a1 into f of x minus h plus a2 into f of x plus a3 into f of x plus h, which is again a central difference formula because it gives you the derivative at x in terms of the function values on either side of x along with the value at x. It is a central difference scheme. So, how will you determine a1, a2, a3? There are 3 constants. So, you require 3 conditions. So, you determine a1, a2, a3 in such a way that the method is exact for polynomials of degree 1, namely constant polynomial, for polynomials of degree 0, namely constant polynomial, for a first degree polynomial and a second degree polynomial. So, you make this method exact for polynomials of degree up to 2, and this will give you 3 conditions, and use these 3 conditions to evaluate what are a1, a2, a3. And once you obtain the formula, then compute the truncation error in the approximation of that method, approximation of the derivative in a way similar to this, and then show that the error is this. So, your method is valid for a class of functions f such that the fourth derivative exists in an open interval x minus h to x plus h, and no, this is h square by 12 into the fourth derivative. So, class of functions f such that the fourth derivative exists in x minus h to x plus h, an open interval, and f prime, f double prime and f triple prime exist and are continuous in the closed interval x minus h to x plus h, and the error is of order of h square. So, try to derive this method. So, I shall give you another example. So, show that f triple prime x, the third derivative, can be given by f of x minus 2h plus twice f of x minus h minus twice f of x plus h plus f of x plus 2h divided by 2h square minus h square by 4 into the fifth derivative at psi, which is again a central difference formula for the third derivative at x, which involves information of the function values at x minus h, x minus 2h and x plus h and x plus 2h. Suppose say you require numerical differentiation methods from which you have to compute the various order derivatives at one end point of the set of information that is given to you. Namely, if suppose the function values f of x, values of f are known at x, x plus h, x plus 2h, etc. And you require, say, the first derivative at this end point x of a set of values which are given to you. Then you obtain this formula using forward differences, namely work out the details and show that f prime at this end point can be estimated by minus thrice f of x plus 4 times f of x plus h minus f of x plus 2h by 2h, and the error involved is of order of h square, and the term f triple prime psi indicates that it must exist where in the interval x to x plus 2h with f prime f double prime continuous in the closed interval x to x plus 2h. So, you observe that the derivative at this end point is required, and it is given in terms of the function values at this, the function value at x plus h and the value at x plus 2h. So, it involves the function values at lie to the right of x. So, it is called a forward difference approximation to the derivative f dash of x. So, you can derive by method of undetermined coefficients either forward difference approximations and analogously backward difference approximations in terms of the values to the left of x, namely values at x minus h, x minus 2h and so on for various order derivatives, or using central difference approximations for any order derivative. So, the method of undetermined coefficients is very useful when you have the information about the function values at a set of points which are equally spaced, and the estimate for various order derivatives can be computed either using forward difference formulas or central difference formulas or backward difference formulas. The natural question comes to you, where are they useful to us? Why are we deriving these numerical differentiation methods? These formulas are going to be very useful when we take up the numerical solution of differential equations, either ordinary differential equations or partial differential equations. But in the case of partial differential equations, we will have to obtain an approximation for a partial derivative. But what we have done in this course or in today's class will be very useful for us in numerical solution of ordinary differential equation. How is it useful? So, suppose it involves, say, a third order derivative or a second order derivative or some 3x times a first order derivative. Say, suppose you will have to solve an equation of this form, right? Then, and you are unable to solve by any of the techniques that is known to you. So, in some interval, say some 0 to 1 or some interval, then you can approximate these derivatives by means of the finite difference approximations, namely the numerical differentiation methods, either throughout by forward differences or throughout by central differences or by backward differences, and so that you know what is the order of accuracy of the method that you propose to solve this differential equation numerically. So, once you have replaced the derivatives by means of their finite difference approximations, then you need to solve the unknown value at a set of discrete points, namely the points x, x minus h, x minus 2h or x plus h, x plus 2h and so on. So, you will end up with a system of algebraic equations and then solve these by the methods which are available for solving a system of algebraic equations. You arrive at the solution at a set of discrete points. So, you get a numerical solution of the ordinary differential equations, and the numerical differentiation techniques or methods that we develop are very useful in solving or in obtaining the numerical solution of ordinary differential equations. So, we shall continue with some more methods for obtaining numerical differentiation formulas in the next class.